So, hi everyone. Today I'm going to present the project I worked on during my internship at AWS. So it's about how we can use deep distributional time series models for anomaly detection. This is a joint work with Lorenzo, Stella, Gasthaus, and Team Januschowski. I will start by giving you a bit of motivation and what led us to develop such a methodology. Then I will give some details, some technical details on how it works. And finally, I will analyze the performance of this method on synthetic and real data. So we start with some motivation. The methodology that we developed was specifically designed for a service monitoring setup. And in such a setup, a metric data is stored whenever a request is handled by a service. So this gives a stream of events where each event will take the form of EK, a tuple, with TK, the timestamp of the request, and MK, a set of measurements. For simplification, we will assume that the measurements MK are real values. And for example, one can think of the latency or the CPU usage or the memory usage as such measurements that we would monitor. And the goal is to detect an anomaly or an anomalous behavior from this stream of events. The specificity here is that the measurements are triggered whenever an incoming request happens. So the timestamps are not equally spaced. So this deviates a lot from the usual time series setup that we know. And the problem is, like, for large services, one may collect several thousands or even hundreds of thousands of events per minute. So the typical anomaly detection pipeline would start with a temporal aggregation into a fixed size time interval, like a meaningful one. It can be 5 minutes, can be half an hour, it can be an hour, depending on the service. But this requires choosing a meaningful summary statistic. Usually, we take some quantiles, for example, the median, or the 5% quantile, or the 95% quantile. Sometimes we also take the mean, for example. The main problem with such an approach is that we can easily miss an anomaly depending on the choice of the summary statistic. To illustrate this point, I took an example from Amazon data. So this is, here we are monitoring the same latency metric, so it's the same underlying set of measurements, but using 3 different summary statistics for aggregation. On the left, we use the 5% quantile. In the middle, we use the median. And on the right, we use the 95% quantile. So if we look a bit more in detail what happens in the 95% quantile figure, at the end of November, we see that there is an anomaly here, the yellow region. However, at the same time, in the median or the 5% quantile, we cannot see anything. So this means that if we had chosen to monitor only the median or the 5% quantile or both, we would have totally missed this anomaly. And this is independent on how good your anomaly detection algorithm is, because the anomaly is just not in the data. So our methodology is basically deals with the problem of this aggregation step, and it tries to circumvent this aggregation step. I will present an overview of or a summary of our approach on this with this figure. So here, if you look at the upper panel, you can see the raw data, the raw measurements. It's this time series in black. So we start by deciding on a meaningful time interval. So let's say here is half an hour, and we will group the measurements into fixed size time intervals, which are represented with the vertical red dashed lines. And so for each time period, we observe NT measurements. In this case, NT is equal to 400. Now, instead of choosing one statistic to summarize these 400 observations, we will represent the whole distribution of these observations. And or like here, simply we will represent the histogram of the observations. So this is the interesting part, is like we go from this set of measurements and we construct from it a histogram. So we observe a time series of histograms. And to emphasize this even more, in the rest of the talk, I will speak about the measurements to refer to this raw data, the black one here, and the observations to refer to this aggregated summary, which is like the histogram or the distribution of the data. The anomaly detection works as follows then. Using a recurrent neural network, we will predict a distribution over the histograms or over the distribution, and then this prediction is represented here by this yellow-red heat map. Then we take the real measurements, we construct the histogram corresponding to these measurements. Here it's represented by this black or blue horizontal line histogram, and we see if it corresponds to the prediction. If it corresponds to the prediction, then there are no anomalies, and if it doesn't, then we say that there is an anomaly. On the left figure, for example, the histogram corresponds to the prediction, so no anomalies here. And on the three following ones, we see that the histogram differs quite a lot from the prediction, so we say that there is a problem or an anomaly. Let's fix a bit of some notations. We will denote by an uppercase Z to refer to the random variable, and to a lowercase small z to refer to an observation or a realization of capital Z. As we said, here an observation is not the measurements, the real-valued measurements, but it's a histogram or a distribution itself. So we will use the classical probabilistic time series model to do anomaly detection. So in order to do this, we need to predict the distribution of the following observation, Z capital T, given the past observation, ZT minus 1, ZT minus 2, etc., and possibly also given some vector of covariates or features. So this distribution of the following observation is called capital PT, and the goal is to estimate this distribution. Now, given this distribution capital PT, we can construct a 1 minus epsilon codable region CT of epsilon. So this means that under the model, the probability of the following observation being in this credible region is equal to 1 minus epsilon. Epsilon, for example, can be 5%, so it means that the probability of the next observation to fall into this credible region is equal to 95%. And if ZT is not, if the observation is not in the credible region, then we flag the observation as an anomaly. As I said, the technical part here is that our observations are a bit more complex than just a real value time series. Our observations are histograms or distributions. So PT has to be a distribution, sorry, over histograms or over distributions. Any anomaly detection method based on probabilistic forecasting is composed of three features which are needed in any case. First, you need to choose a class of distribution from which PT will be an example of. So I will refer to this as the probabilistic model part. Then you need to define the temporal dynamic, which means how does capital PT depend on the previous observations. So this is called the forecasting module. And finally, you need to show how you can construct a meaningful credible region CT epsilon. And this I will call the anomaly detection module. When NT is very large, we can suppose that we directly observe the probability vector PT. And just because when normalizing the histogram, we get a very good estimate of it. And therefore, the observation, our actual observation, is a probability vector, is this PT. So we need to design a distribution over this PT, so over the probability vectors, so over the D-1 simplex. And the natural choice for this is to use the Dirichlet distribution, which is parameterized by this vector alpha t with the positive real entries. When NT is small, we model the frequency histogram MT using a Dirichlet multinomial distribution. So MT is sampled through a Dirichlet multinomial with parameter alpha t, still positive real entries, and NT, the number of measurements during that time period, and this NT is known. So this procedure can be seen as a two-stage process. First, you sample the vector PT from a Dirichlet, and then you draw NT measurements from it. So our model is coherent in the sense that when NT goes to infinity, the Dirichlet multinomial model will, of course, converge to the Dirichlet model. And it is good for us because everything is summarized in the end by this vector alpha t. And what we need to model now is the dynamics of this vector alpha t. So now let's look at the forecasting module. So this is done using a recurrent neural network, and as we said, what we need to be predicting is the vector alpha t. And so we need to define how alpha t depends on previous observations. And this is done through a recurrent neural network, as I said, where here zt are the observations, and it can be either probability vector when nt is large or a histogram, and xt are a vector of covariates, and we use the log likelihood as a loss function to train our model. This model is very close to the deep AR architecture that has been developed by Amazon and has proven to be very efficient for time series forecasting. So once we forecast alpha t, the question is how do we assess if zt is an anomaly? And as I said previously, this boils down to deciding which credible regions to consider. And in our case, we chose to use the level sets of the likelihood. And these level sets are basically defined as the highest density region that would achieve a total mass of 1 minus epsilon. So it's the set of all possible observations whose likelihood is larger than some threshold eta, and such that the probability of the observations under the model of falling into that level set is equal to 1 minus epsilon, so 95%, for example. In the end, the decision rule is really simple. You look at the observations at t, you compute its log likelihood, and if it's smaller than some threshold eta t, you say that it's anomalous. And eta t is constructed using a Monte Carlo method. Okay, here is an example of, or rather an illustration of this level set method. So here we are considering a random variable with two coordinates, and the red surface is the log likelihood of this random variable. The blue plane corresponds to the threshold eta that we are selecting. And basically, we are considering that all the points whose likelihood is beneath that plane, that blue plane, are anomalous. So from left to right, we have three different values of eta. From left to right, it's getting larger. And on the top, we can see the credible region that it corresponds to. And we can see that it can construct quite complex geometries, even though in the end the decision rule is really simple. We just need to see if the log likelihood is larger than the threshold or not. Now we'll have a look at the performance of our model. As a sanity check, we consider a synthetic experiment composed of two datasets. These two datasets are normal distributed, and it's sinusoidal, so the mean behaves as a sinusoid, and the variance of these normals are just equal to 1, it's set to 1. Now we also add some noise over this to make the prediction task a bit more complex, and this noise is just like a normal with variance 0, 1. The noise can be added to the mean or to the variance. On top of it, we add 3% of artificial anomalies, and these artificial anomalies are either by shifting the mean, like adding 1 to the mean at a time point, or a dilatation of the distribution, so a dilatation of the standard deviation, or basically multiplying it by 2. We learn over t is equal to 1,500 time periods, and for each time period, we have access to 1,000 measurements. Once we learned on this 1,500 time intervals, we do the detection on the following 2,000 time points. So here, the thing is, if we wanted to use an aggregate statistic, we know that we should be looking at the mean and the standard deviation. We compare it to two state-of-the-art algorithms, namely Twitter AD and Luminol. Twitter AD is developed by Twitter and Luminol by LinkedIn. And we report here the AUC metric for the evaluation. For Twitter AD and Luminol are, let's say, the classical time series objects. So they would need you to choose a summary statistic before feeding them the data. And as I said, here we know which summary statistic to look at. So we feed them, actually, we give them the mean and the standard deviation. Of course, this is not realistic because in a real life setting, the whole problem is that we don't know which statistic to monitor. And in our distribution approach, I call it here distribution, of course, we don't need to specify this. And we can see that even though our approach doesn't know which statistic it should be looking at, it still outperforms the Twitter AD and the Luminol on average. So here is an example of the anomaly detection part. So we can see in red is the actual observed signal. So it's the distribution of the data at a given time interval. In blue is somehow the credible region, so the predicted region by our model. So if the red line falls into this blue heat map, then there are no anomalies, sorry. And if not, then there is an anomaly. So here we can see that the red line falls well inside our prediction. So to make sure of this, we look at the distribution of the log likelihood predicted by our model if no anomaly were to happen. So the black line corresponds to the eta threshold. If the likelihood is under this eta threshold, then we consider the observation as an anomaly. Here we can see that the red line, which corresponds to the likelihood of the observation, is actually over the black line, so there are no anomalies. Now, on the contrary, if we look at a time interval where an anomaly happened, we can see that the true observation, sorry, is very different from the prediction. And this, we can also see it on the log likelihood distribution, and we can see that the observed log likelihood is way beneath the acceptance threshold. So here there is an anomaly. Now we also looked at some real data, for this it's Amazon AWS data, and it's composed of 3 benchmarks. The first one is 1 minute data and composed of 55 time series, sorry. The second and third one are 5-minute data composed of 100 time series each. For our distribution method, we use half an hour as the time unit. So we aggregate them every half an hour. So this corresponds to n is equal to 30 for the first data set and 6 to the other data sets. We learn on the 60% of the data. So this is for training. And the rest is used for detection. We again compare to Twitter AD and Luminol. And we can see that here again, our approach seems to outperform quite heavily the competing methods. So as a summary, we proposed here a novel anomaly detection method, which is based on distributional time series models. The whole point here is to avoid the aggregation, temporal aggregation step, not to miss any anomalies. Besides, our method has many advantages. First, it's unsupervised, and this addresses the lack of label that we observe in real life situations. It's scalable, both in terms of computation scalabilities, but also in terms of the need to involve experts to tune the system. And it's flexible. It can handle different time series and different anomalies. For example, CPU usage, latency, error rate, or anything else. So finally, this method builds on a predictive model for a distributional time series representation. And it employs an autoregressive LSTM-based recurrent neural net and gives flexibility while still being statistically sound.